Okay, so today's subject is very important. It's a stability of structure. Stability of structure. So actually this is a subject for one semester in many schools, but because we don't have time, so in this just one class I'm going to introduce the concept, essential concept. Okay, so stability of structure. So many cases people don't know what's the stability, and many students doesn't know the difference between stability and safety. Safety, both are different. So this is a safety is a 안정성, stability, 안정성. So one looks very similar, right? But both are really different things. So you know the safety means determine the whether structure fail or not. So it has a more bigger meaning than the stability. Stability, it has a different meaning. So, for example, let's say we have some structure looks like this, and I'm going to put this on the ground. And the other case is this. Here I have a structure. Which one looks more stable? This one, A, B. Yeah, everybody know that this looks stable, right? More stable, right? How do you determine why this looks stable? More stable. Why? John, why? Why do you think like that? Why? Center of gravity is lower. This one is yeah, that's true. Is that all? Okay, so for example, let's say I'm going to push at top point, lateral, I'm going to give some lateral load, very small lateral load. Which one is? This one is very hard to fall down, right? But if you push a little bit, it will fall down, right? Easily. Okay? This is the concept. So, this falling down is also failure, right? This is not a failure of material. This is not a failure by yielding, right? Of member or material. So this is totally different thing. This is it's really related with the geometry. So, in many textbooks, explain stability with some ball. So here I have a ball, and if I push this ball, this will move, ball move, right? And then if I remove the load, it will go back to the original position, right? So if I push this structure, then it will rotate it a little bit, and if I remove the load, it will go back, right? And the other case is this. Flat bottom. So if I push this ball and remove this ball, move to the other position, and if I remove the load, this ball will stay here. Okay, and the other case is this one. If I push this ball move, continuously move, right? Even you remove the load, right? So this small additional load is said to be a perturbation. Perturbation, okay? It's a perturbating load. So in this case, if I push with a small load, this will easily fall down. Of course, if the load is very big, it can be also fall down. But the level of the perturbation force is different. So that perturbation force to make this structure fall down is big. We can say this is stable. It's small. It's not stable. So we can measure the stability like that. So we are saying this is stable. And because it go to the, when unloading it go to the original position. So in this case also, if I unload, it will go to the original position, right? And this case is unstable. And this case is a neutral. A neutral case. So this neutral case is really ideal. Okay, this is a concept, and I'm going to give you concept of stability of structure with an example. Okay, so I like say illustrative example. First, let's consider bar. This is a rigid bar. And here we have hinge. Okay, so this bar can rotate. And here I'm going to put some rotational spring. This is rotational spring. With spring constant K. And this bar is perfectly vertical, rigid bar. Actually, it's in realistic case, it's impossible to make a perfectly straight bar, right? Perfectly straight bar we cannot make, but we assume this situation here. And I'm gonna push the force P. Okay? And also, I like to measure the theta. Theta is a rotation of the bar, right? Then I'm going to plot theta P, the load displacement curve. So this load displacement curve will give us equilibrium path, right? So, can you draw load displacement curve for this one? So, not first load is 0. Then how about the theta, 정호? 0. So load become 1 Newton. Then how about theta? Is it rotated or not? No. So even you increase the load, theta will be always 0, right? This is load displacement curve. Very simple, right? Very, very simple. Everybody understand. So this is a load displacement curve. Okay, so this is a load displacement curve, and we are saying this is equilibrium path. Right? Why this is equilibrium path? So when the theta, the position of theta and P is on this line, this structure is always equilibrium, right? So this is equilibrium path. Okay. Now, let's change that problem a little bit. Okay, second. So same problem. Okay, P is applied here, same problem. And, okay, the length is L. The length is L. Same problem. But I'm going to apply very, very, very tiny small lateral pulse. Very, very small pulse. So here P is a very small disturbing pulse. So this is very small. So because even this disturbing pulse is very small, there are going to be also very small theta will happen, right? Rotation, right? So theta is also theta is a very small rotation. Theta is also small rotation. Okay? Okay, then, okay, in that situation, P will be applied here, right? Because of that very small force. Now, let's calculate the equilibrium equation. So, this one is okay. And how about the momentum? Momentum from here will be L theta, right? And let's calculate the moment about here, m0. So this is plus. Let's say sum m0. Sum plus m0 equal, okay, if this barge rotates in this direction, this spring will give us moment in other direction. So k theta minus pl theta equal 0. This is equilibrium equation, right? PL theta is moment due to the vertical force P. Okay? Then let's write down this equation. So theta K minus P L equal 0. So solution, we have two solutions. One is theta equal 0. The other is K minus P L equal 0. Solution will give us a load displacement curve, right? Equilibrium path. Because this is equilibrium equation, so this one equilibrium equation gives us two solutions. The first solution and second solution. So if I plot both solutions here, and theta P. First solution is this one, just this one, right? This is first solution. How about second solution? Second solution means P equal LK. So second solution is this. This is theta equal 0. Second solution, P equal L over K. We are saying this L over K is a critical load, PCR. Okay, so we have two equilibrium paths, right? Two equilibrium paths. If you increase the load, okay, theta can be always 0, and at some point, theta can be increased very rapidly with some rate. Right? Understand? So we have two equilibrium paths, and then that's the divide at this point. We are saying this phenomenon is the bifurcation, and this point is a bifurcation point. Bifurcation point. And theta equals 0 is a fundamental solution. Yeah. So you should remember there are two possible equilibrium paths. And two paths meet at bifurcation point. So structure, if structure doesn't have a small disturbing force, the equilibrium path will go to this way. And if it has a very small disturbing force, it can go this way and this way. It can go this way, both way. So this is a bifurcation. Maybe you don't understand until what's the bifurcation here. Okay, so let's consider three cases when P equal PCR. When P equal PCR. So first case is this. Here I have a load and P is applied. So I'm going to apply the vertical force P, which is smaller than PCR. Here, PCR equal L over K. Okay? Then I'm going to give perturbating pulse P. Then this one will rotate a little bit with the angle theta. Okay? And if I unload, this bar will go to the original position. Okay? So we can understand that behavior in this curve. Okay? In this case, in the theta P curve, this is PCR. Okay? Here, okay, and actually that theta is very small, so we can understand. If we load, it go this way, and unload, it go back. Okay? And second case, when P equal PCR, what happened? If the P equal in PCR here, okay, if I load P, it will go to this way, and unload and go back to unload, it will go back also. Okay? But even you load P, say that PCR, after it will rotate then, when the P, so here the unknown is this one is unknown. So perturbating load is unknown. For the first case, it will go back to initial. Here, when P equal PCR, perturbating load is unloaded then. So unloaded then, this bar will stop at this situation, P. Okay? Doesn't go back and stop at this situation. Even you unload that perturbating load. And third case, P is bigger than PCR, then if we give a perturbating load, then it will rotate with undetermined rate. So, third case, if the P equal bigger than PCR, it rotates, it falls down. This is dynamic phenomenon, actually, collapse. So here the PCR is a critical load. Actually, we are saying that's the buckling load. Buckling load is very important. If the applied load is smaller than buckling load, we are saying structure is stable. But if the load applied is bigger than buckling load, it collapses. We are saying that's the buckling load. So, understand? Any question? No idea? Don't understand? So first we need to understand this bifurcation curve. Okay? And second, we need to understand the meaning of buckling load. Okay? This is a buckling load. So, for example, you think like this. I'm going to give you an example. Here I put some bar here, and here I put some mass on top of there. Here small mass is 1 ton, 100 ton. Okay? This is a applied force from the top. And I'm giving some perturbation. Okay, and here we think here spring. So actually, even we didn't put the spring here, the behavior at this point looks like spring, right? Because we have foundation. Okay, it's spring with very small rotational constant, right? So this case is much more unstable, right? So for example, PCR equal 10 ton. So in this case, even you perturbate, even you giving the perturbating lateral force, this will go to the original position. So, and in this case, this structure doesn't buckle. But in this case, it will fall down, right? Because of the load we have on the top of your head, right? Okay, so through this point, through this illustrate example, maybe you can capture some very important thing. This kind of buckling phenomenon happen in compression case, not the tension case. Okay, so applied load P compress this member, right? Okay, so this is also failure mechanism, very important failure mechanism of big structure. So actually, big structure usually fail due to the structural stability rather than material failure. So usually large scale structure fail due to the stability first, then there are going to be some yielding. Okay, so failure due to the stability first, then failure due to the material. Okay, it's a sequence. Okay, so actually this stability phenomenon can be explained by dynamics, but I don't want to skip. And Today I like to talk about stability of column. This is really basic thing. Or column. So column is a compressed bar. You know column, we have a lot of column in this building, right? So let's consider column, simple pinned column. So it has a hinge at the top and at the bottom. Here roller, P is applied here. So Y, X. Okay. Now I like to calculate buckling load of this one. And this is a initial position. And for example, I'm going to give very tiny small perturbating load. And this load, actually originally without this perturbating force, this bar cannot be bended, right? How? It cannot be bended. But if I applied very small perturbating force, this will be bended like this. Right? Very. And let's say this is a displacement B. And let's consider the part of that bar. Okay, here P is applied here. Then moment, internal moment M is applied, and from here to here, this is a B due to the small perturbating load. Okay, then here moment should be 0 for this free body. Then M plus PV should be 0. This is equation from the moment equal 0. So let's say this point 0. This will result in the equilibrium equation for moment. Okay. So to calculate to find the buckling, to perform the stability analysis, first time we need to consider some perturbation. Okay? So this is a perturbation due to the very small external load. Okay, there are many kinds of different perturbation. But here I applied small force, and then M also is a function of EI and dx square. Okay, this is from the Euler beam theory. Then finally we have an equation, ordinary differential equation, V, second order ordinary differential equation, EI PV equals 0. This is the ordinary differential equation with boundary condition B0 and BL equals 0. This is the boundary condition. So we need to solve this equation. And for this ordinary equation, the fundamental solution is this. B equals C1 sine mu x plus C2 cosine mu x with mu equal PEI. Right? This is the fundamental solution. And if I apply the boundary condition in that fundamental solution, we can easily find out C2 equals 0. Then we become C1 sine C1 sine Vx. This is solution for displacement. Okay. And then this one gives us two different case. One, C1 equals 0. This is first case. And the other one is sine mu x equals 0. Okay, let me see here. Okay. Okay, maybe I need to put this one. Okay, then if I consider both, this one give a mu equals 0. This is a fundamental solution. And second one give us different solution. Mu L equal E I P L equal n pi, because sine function becomes 0 when the mu L is n times of pi. So these two solutions from the when you apply the VL equals 0 to the second boundary condition. So this first one comes from the V0 equals 0. So to satisfy this boundary condition, okay, we have two cases. So we need to consider these two cases. First case gives us fundamental solution. So no bending, the transpose deflection. So this was fundamental. Second solution is this. Okay? Okay. So that second solution gives us equation P equal EI L pi n pi square. Okay? And there are a lot of solutions, right? Because n is a integer number. But from all the n, possible n, and start from 1, 2, 3, 4, right? When the n equal 1, that load P is smallest. So PCR is defined by EI L pi square when n equal 1. This is a smallest critical buckling load for the column. So we can draw also curve between P and V. Let's say V max. Then first equilibrium path due to the here fundamental solution is that this one, because V equals 0. And second one is this one here also. This is a PCR. So beam, column, lose the stability when compressed load is bigger than buckling load PCR. And really interesting is that here PCR doesn't depend of strength. It depends on, this is failure load, again, understand? It depends on Young's modulus and I, second moment of it. It's from the geometry. L is a geometry. No strength, right? This is very important. So, okay, stability comes from the geometry, right? Doesn't depend on the strength. You know the strength, material stress, yield stress, right? So, for example, let's say here we have a slender member. If I pull this member, it fails by yielding, right? Plastic yielding. But this slender member is compressed, but then failed by buckling load. So it fails like this. So failure load is different. Right? Okay? So for slender member, this PCR is smaller than PY. So here we have the same member. And I'm going to compress and I'm going to stretch it. But in compressed case, it's easy to fail due to the yielding phenomenon, so buckling phenomenon. But when the member is stretched, the tension, there is no problem of stability. Okay, understand? So, for example, in this case, here I have a very rigid bar here, and two member is applied here. Both are bar. And I'm going to here compress. I'm going to give some torsion. Then this bar will be tension. This bar will be compression. And if I assume both bar have a same length, same cross-sectional area, which one fail first? Of course, this one fail first. It will fail like this. And so failure is governed by buckling. Okay. Actually, this buckling load depends on the boundary condition. Here I consider the pinned, right? Both are hinged, right? Hinged. But it depends on the boundary condition also. So for example, for the both rigged case, here we have a both pin case. Buckling load, PCR. This case, buckling load is bigger. And this case, it buckling shape is like that. And this case, buckling shape is like this. So, okay, so maybe you can find the equation about the buckling load depending on the boundary condition in many textbooks, right? It's very easy to find. Even in the internet, you can find it. And here, now, I said, if here the beam column is perfectly straight, then it cannot be buckled, right? It cannot be bended under the compression load, right? But in real case, that kind of perfectly straight bar column, we don't have that kind of perfect thing, right? So it's buckled, always buckled. So we are saying that kind of so we are saying that's the imperfection. So there are many kind of imperfection. So one is that geometrical imperfection. So here we have a column. So we want to make really perfectly straight column, but in the real case, it's a very slightly bended already, right? Then we are saying this is a geometric imperfection. So imperfection. We are saying imperfection. And the other imperfection is that here, let's say even this column is perfectly straight, when we applied load at the exact center, then it's not bended. But we cannot do that. So always there are small eccentricity. This eccentricity is also imperfection. And also the other imperfection is a material distribution of material property. So if we assume the material is homogeneous, so at all the each material point, we have the same Young's modulus, and if we have a same Poisson ratio, it's a really perfect material. But our real material is not like that. So that's also imperfection. So due to this kind of imperfection, so column buckle. Okay? So maybe I need to stop the lecture here.